Good morning, everyone. My name is Daniel Tan from Aura Protocol. It's the Aura Protocol that got mentioned in the last session. Um, Today, I'm going to present a topic on zkVM from today to tomorrow. So first, I will provide an oversimplified mental model for you to construct a zero-knowledge proof. So in essence, build a zero-knowledge proof system just need two steps. First, you need to build a snark or a Stark system. And the second step is to add zk to enable the privacy features. And let's see how to build a modern zk snark. So a typical modern snark has four pillars: circuit arithmetization, polynomial IOP, polynomial commitment scheme, and optional folding scheme. So you can see the zk proof system itself is quite modular. And under each pillar, there are several options that for us to choose from. So for example, we can choose Plonkish with quotient testing, polynomial IOP, and KZG to build a zk snark. And you can also try different composition to build a different snark or a Stark system. We also need to build a virtual machine. A virtual machine is just a program that emulates a physical computer that runs another program. So now we have a zk proof system, and we have a virtual machine. We have a zk virtual machine. So in simple term, a zk virtual machine is just a virtual machine that implemented as a circuit for a zk proof system. So to build a virtual machine, you can also choose from several instruction set. So in this talk, we are going to focus on the mainstream instruction set, which can be considered as a general purpose zkVM. So inside of the mainstream instruction set, we have WASM, RISC-V, and MIPS. So every one of them has a richer ecosystem than the Web3 ecosystem as a whole. So by building a zkVM with the mainstream instruction set, we can enjoy their richer ecosystem. And the purpose of a general purpose zkVM is to be able to generate proof for any program in any language. By any program, I also mean another zkVM. So it's very interesting that we can build another zkVM inside of zkVM. And also, it's also very relatively simple in a sense that we can use a relatively small set of constraints to describe the whole VM. And in this era with Sora and incoming AGI, zkVM can definitely help us to ensure the accountability for AI-generated content. So with so many benefits that zkVM brings to us, the only cons is the performance issue. But luckily, we have three major ways to tackle this problem. So the first is we can try to apply some optimization tricks under the current architecture. The second is we can continue to research on novel techniques and better frameworks to build zkVM to make it faster. Or the third one is hardware acceleration. So if we can solve all this performance issue, a perfect zkVM will be the adoption for the Web3. So according to this report by Developer Nation, the number of Web3 developers among all the developers in the world is actually less than 0.1%. In a world with a perfect zero-knowledge VM, we can target all the developers in any language and supercharge their program with the power of the zk. Let's also talk about a little bit about the current landscape. We start to see the commercial zkVMs coming out after 2021. In the last market cycle, we can see a lot of zkVMs coming out tailored towards proving the execution of EVM, aka zkEVM race. And also we can see Definitely Lab and RISC-0 is leading the development of general purpose zkVM for WASM and the RISC-V instruction set. In this current market cycle, we can see on the right-hand side, there's a burst of zkVM projects coming out. Some of them use novel techniques from the research to try to build a better zkVM. And some of them are pivoting from the other track. And some of them are just trying different combination of the current stack. But there's definitely more projects coming out. And this is just the start of the zkVM race. So let's dive in and see how does the zkVM work. So similar to how does zkEVM work, so where you can only write programs in Solidity and get it compiled to VM bytecode and send it to zkVM and get a proof for the execution. So for zkVM, you can actually write any program in any language and get a proof for the execution. This sounds a little bit too good, right? So you must have a cost for this generality. So the cost is proving inside of zkVM is generally 10 times to 100 times slower than a specific purpose VM. So on the current architecture, the optimization strategy is mainly twofold. First, we can apply some general optimization tricks on a language level. And the second is we can adopt a hybrid approach. So I will use event proof flow to illustrate the optimization strategy I just mentioned. So to prove the target event is actually included in the block, first you need to do is to initiate a RPC call from your node provider to get the decoded RLP receipts. So next you need to do is to apply RLP decoding on every encoded receipts you have, and then get a raw receipt. So for raw receipts, you can apply some filters and to process it to find your target event. But in order to prove that your target event is actually included in this block, you also need to construct entire MPT tree. And if the constructed receipt route is actually matched with the receipt route in the block, then you can be confident that the event is inside of the block. This is an example of a provable program that you can just throw into zkWASM and get a proof. But this will work for historical access, but this will probably not work for if you want to access the recent blocks, because it's gonna be pretty slow. So we need to apply some optimization strategy on this. So the first strategy is the general approach. This is a utility function that we encountered during the event proof flow. The function is called bytes to hex. And basically, we just replace some of the plain string joint with this string method called charcode add, and to remove some unnecessary immediate process. Here is the result. We can see there's a very significant improvement on the performance, particularly on if the string is very long. So next is the hybrid approach. zkWasm is providing this host VM architecture. So basically, host VM is another VM inside of zkWasm. And I believe there's some similar architecture for other zkVM as well. So the basic idea is if some operation is considered as a bottleneck, we can replace the operation with a host circuit. So in event proof, what kind of operation can be considered as a bottleneck? So we have a lot of, we need to decode every encoded receipt. So we have a lot of RP decoding operation. And inside of RP decoding, we also need to do a lot of caching algorithm. So those are crypto primitives that are considered very hard for a general purpose zkVM to do. So we can write some host circuits for it. And also, zkWasm is providing this continuation batcher, so we can batch all the host proofs and the guest proofs together to generate the final proof. And I'm also preparing like a sequence of tutorials to teach the developers on how to write the host circuits. So next, I'm gonna present some novel use case that zkVM brings. So the first use case is programmable zk oracle. So similar to the event proof I just described, our protocol is able to prove the access to all the historical data on Ethereum. And with the power of zkVM, our protocol's computational logical entity is able to perform complex and arbitrary computation and get it the proof with zkVM. The next use case is a provable game. So Blade Games is building a provable game framework with Unity and zkWasm with their game engine native and zk server approach. So under this framework, game developers can continue to work on their favorite environment, like C#, and continue to develop their games there. The game code in C# will be decoupled into two parts. The first part is core game logic, and the second part is the rest of the code. Both of the parts will be compiled into Wasm bytecode, and only the core game logic will run in zkWasm runtime. And zkWasm will generate proof for the execution trace. And, but the rest of the logic will run in your local C# runtime, so you don't have latency for the rendering and stuff. So this is a very simple PvE tower defense game where the enemy comes in waves. So first you need to do is, so in this setup, the map setup is considered as a core logic. What you will need to do is to confirm your map setup and commit the map setups on chain. And for the rest of the waves, you don't need to do anything in zkWasm, and you can just run in a local runtime. Before the next wave, if you want to change the current setup, let's say if you want to change the coordinate or upgrade the turret, then you need to commit again. Otherwise, you don't need to commit. So in this approach, you can enjoy like near Web2 gaming experience. Next is zk compiler. So zkGo is a zk compiler for the Go language. Go language is considered as like particularly important in the crypto space because the most popular Ethereum client is implemented in the Go language, and as well as the layer 2 OP client. So there is a very interesting use case that you can actually compile the layer 2 OP clients into Wasm bytecode and get it approved in zkWasm. So this is act as a zk processor, co-processor for the OP stack. So by creating this zk floor proof, which is a validated proof with immediate finality, you can actually shorten the waiting period of optimistic tech stack. And also you can use it to replace the multi-interaction dispute game, which can be sometimes very expensive. Also, we've encountered some challenges for the zkVM, particularly with the increasing popularity of AI cross crypto due to the incompatible number system. So as we all know, AI use a floating point number system. That's why the AI model can be very powerful because they can learn from the very little amount of the gradient. And the zk system use finite, you work with a finite field, which is essentially a fixed point number system. A very naive way is to present the floating point number inside of zk circuit, but this introduces like a lot of extra variable and increase the complexity of the proving system. And the current approach is called quantization. So quantization is basically means to map a continuous number into discrete number. There's two approach for that. So some project is using a soft float, which is essentially use software to emulate the floating point inside of zk system. And another is called circuit quantization. This is just to scale up the floating number and apply a floor function. So you will discard all the fraction part of the floating point, and this will cause the decrease of the accuracies for sure. So we definitely need more research on this area to make it better. So let's go back to the performance issue. Here is a novel approach that proposed by some zk researchers at Z16Z. This approach is called joint and lasso, and sometimes it also refers to lookup singularity approach. The basic idea behind this is just to prove every instructions use table lookups. So this will increase a lot of efficiency in the system. So all aspect of zkVM is proving so quickly. Just several days ago, there are two projects that announced that they can able to prove the game of Dome. The Dome is a first-person shooting game, and it's considered as a very hard problem to prove in zkVM system. So this marks as a very important milestone for the zkVM to be able to use in the industrial setting at a scale. zkVM is converging to a point that the real use case will happen, and is surely leading the wave of the next wave of massive adoption for Web3. Thanks for listening. This is all about my presentation, and we are hosting an event on 27th. That's about the AI cross crypto. You can scan the QR code if you are interested. Thank you.